In this video, we're going to start chapter 11, which is about waves. So to motivate this wave stuff, I want to give you guys a little kind of cartoon picture of how we can think about a wave. So for our oscillations, we talked about a mass connected to a spring, right? And we saw that this system, if we pull it down and let it go, this system will oscillate up and down on its own. Now imagine that we have some masses, like a bunch of masses. And these masses are all connected by springs. So let's imagine that I take this mass and move it to the right a little bit. So I give it some displacement to the right. Now it's going to compress this spring. That spring is going to in turn push on this mass and give it a force to the right. That's going to cause this mass eventually to accelerate and move to the right and compress this spring, which is going to push this. Anyway, so the point is, if we cause some displacement here, that displacement propagates through this system. So we start with a displacement, and somehow that, that push here causes a push on this, causes a push on this, causes a push on this, causes a push on this. So this displacement propagates from one end of our system to the other. Of course, if we're actually studying what's going on in this mass spring system, there's a lot of interesting things that are going to happen that we don't have time to get to, but this is at least introducing the idea that this thing, this displacement traveling through this, is going to do so at some velocity. In other words, if we push on this, we don't instantaneously get this other one to move. We have to accelerate this mass that compresses this spring, and then that accelerates this mass. So it takes some time. So there's this displacement here moves with some velocity. And that velocity depends on properties of our system. In this case, for this cartoon, it's going to depend on what these masses are. It's going to depend on what these spring constants are. And we could, with some time, we could figure out what that velocity was in terms of those. We're not going to worry about that in this case. So this is the idea of a wave. A wave is a displacement that propagates through a system. And this displacement can look like lots of different things depending on what kind of system we're talking about. So for example, we can have sound waves that travel through air, where our displacement is gas molecules getting, if they get pushed to the right, they kind of can get bunched up near these. So this is supposed to be like gas molecules that are bunched up. This is gas molecules that are further away. And if we, push on these and compress them, they are going to move to the right and compress their neighbors and so on. So you get this kind of moving region of higher density molecules that travel through the air. We also can look at sound waves and other things like like liquids and solids are basically the same picture, although the molecules aren't, maybe they're closer together. We can also look at something like waves on the surface of water, where we have flat water, and then there's some higher piece of water that has some velocity to the right, and as this moves to the right, it the water here can. As this water moves to the right, the water level here is going to decrease, and the water level over here, as the water goes that way, is going to increase. So you can see this same sort of thing. It's the displacement of these of this water, of the surface of the water up or down as this wave travels across it. And the one we're going to actually focus on the most is something that we don't see so much, but you can hunt around and look for examples of it. This is waves traveling on a string or on a rope. So if you're holding one end of a rope and you whip your hand up and down, you can kind of get a little, blip, a little bend in the rope, and this can travel down the rope with some velocity. So we can do careful controlled lab experiments where we can actually measure what this velocity is, and we'll have more to say about that later on. But this is actually a really nice system because it's really easy to analyze. All right, other kinds of waves we will talk about later include seismic waves. So those are like sound waves traveling through the earth from earthquakes. Light waves, so light and radio waves are all a form of electromagnetic waves, and we'll talk a little bit about those also. Yeah, great. So there are all kinds of different waves, and what we're going to learn about is the rules that all of these obey. Okay, so waves can have lots of different shapes. So like I said, this person who just waved the rope up and down, they made this little like bend shape that's going to travel down the rope in that direction. This is called like a wave pulse. We're not going to focus on those so much. What we're going to focus on more is if we imagine this person moving their hand up and down continuously in a, like a simple harmonic oscillator, they're going to make a wave on the rope that looks like a sine wave that is traveling to the right. So every point on this sine wave is moving to the right as this happens. So this is the kind of wave we're going to focus on first in this course. So so this is a sine wave, and in particular we'll call this a traveling sine wave because it is moving to the right. We will learn about waves that are not traveling later on in this course. Okay, so our waves are these sine waves that we're going to talk about first. So for this sine wave, this person is making this wave by moving their arm up and down at some frequency f, right? Or they're moving it up and down and back to where they started, and the time it takes is one period, right? So we can think of what's going on here at this one spot as a simple harmonic oscillator sort of thing, this sinusoidal up and down motion. Okay, so as they do that, they're generating this wave that's traveling to the right. So at one moment in time, our wave might look like this. At some later moment in time, our wave might look like this, where now every point on the wave has moved that far to the right. So we can see that, our wave has these peaks and it has these troughs. So it has these maximums and these minimums, and also some places where the displacement is equal to zero, right? Where the rope is at this zero height, it has not moved up or down. And you can see, like, as this wave shape moves to the right, it will travel a distance of v times t in some time t, right? So if this is t equals 0, sometime t later, it will have traveled a distance of vt. Okay, if we wait long enough, eventually this peak, which started here, this peak is going to go from here to here, all the way back to this next one. Or I say all the way back, all the way forward to this next one. So after some certain amount of time, this wave will have traveled the distance between two of its peaks. This distance is given a special name. This is called the wavelength. And our wavelength has a variable, a Greek letter lambda, that looks like this. And so that is what we use for the wavelength. It looks kind of like an upside down Y. Okay, so we can figure out what this wavelength is in terms of some things that we already know. So remember, this person over here is moving their end of the rope up and down with some frequency f. So when this wave has moved from this point to this point, that means that whatever's going on here has to look the same as it did when this started. Or in other words, our wave is going to travel this distance lambda in a time equal to the period. I guess I should say in time t equals capital T, the period. So in other words, lambda equals v times t, or v over f, because t is 1 over f. We can rearrange this to give us our first really important wave equation, and that is, so if I solve for v here, multiply both sides of this by f, I get v equals f lambda. So this is true for any sinusoidal wave, whether it's seismic waves or sound waves or light waves or whatever. The velocity of the wave, the velocity the wave is traveling with, is equal to the frequency of oscillation times the wavelength, times the size of the wave. All right, I guess I didn't explicitly say this, but our wavelength is a measurement of distance, so it has units of meters in SI units. And this relationship between wavelength and frequency turns out to be important. So different waves can have different properties depending on their wavelength or frequency. So for example, a sound wave, this is just as an example, a sound wave can have different frequencies. And those frequencies, in terms of what we hear, correspond to different pitches. So what we would call, low notes, like low notes on the piano or whatever. Those are notes with low frequency, with small values of f, and as we will show later on, therefore large values of wavelength. So low frequency means big wavelength. So in terms of actual numbers, we'll get to actual numbers in a later lecture, but low notes on the piano might have wavelengths of many meters, many meters long. So the actual size of the oscillations of the air molecules are very large. High frequencies are going to have shorter wavelengths and maybe in the 10 centimeters or less kind of range. And we could do this, we could write down similar things for all kinds of different waves. I just wanted to give one example where there's a property of waves that we can readily observe, like the pitch of musical notes, and there is a physical measurement. There are actually two physical measurements associated with that, both the frequency of oscillation, like in hertz, and the size of the wavelength in meters. All right, there's another important property of waves that we'll talk about, and that is the amplitude. So this whole frequency wavelength, what's going on in this direction of our wave, is totally distinct from how big our wave is this way. So if we're thinking about moving this string up and down to make this wave traveling on the string, whether we move it up and down a little bit or whether we move it up and down a lot, that determines the amplitude of our wave, like literally how big it is in this direction. So this is like, this is similar to the amplitude of our simple harmonic oscillator, right? Our mass bouncing up and down from the spring, it can bounce up and down a little bit, it can bounce up and down a lot. And in the case of the mass spring, that didn't affect the oscillation frequency. So similarly to that, whatever the amplitude is here doesn't necessarily have anything to do with the wavelength and frequency. Those are kind of independent properties of the wave, and we can change one. Most of the time we can change one without changing the other.